Hello, everyone. This is Ming from Momentum Learning. In this session, I'm going to review the 3 questions in the 2023 January round of the USACO contest. Question 1, find and replace. Question 2, following the directions. Question 3, move route. Let's start from the first one. Find and replace. Here we're given T queries. In each query, we're given 2 strings. S1 is the original string. S2 is the final string. They have the same length. Each time, we can replace one letter, all the occurrences of one letter to another letter, also in the alphabet, can be lowercase, can be uppercase letters, and asks how many times it needs to take so that we can go from S1 and arrive S2. So if S1, S2 are already the same, then the number of operations would be minimum. If, like this one here, you have A, B, C and B, B, C here. So don't have to change the B's, don't have to change the C's, just change the A to B's. So this will take 1 step. Sometimes maybe it's impossible here. Why? Because you have S1 that's BBC and S2 that's ABC. So if you want to change the B to A here at position 0 here, then the B at position 1 also should be changed to A. So it's impossible. So this is actually the first observation. If you noticed in S1, there are 2 letters, 2 occasions of the same letter. But if they have to map to 2 different, so this is triangle, this is a square, then you know this is impossible. So this is like the mapping. Mapping has to be unique. If you apply the rules, every time you replace all the occurrences of one letter with another letter, so it's guaranteed if the input is the same, then the output must be same. But in this case, if the input is the same, but output is different, so it's impossible to have a sequence of the mappings. So in this case, just return -1. If you have a cycle, so here A goes to B, B goes to A. So here A goes to B and B goes back to A. We cannot simply just apply for all the A's, replace it with B. So if that's the case, A, B, C, D, if you replace all the A's with B, then you would get B. B still stays the same, B, B, C, D. Next time, if you replace all the B's with A's, then you would get A, C, D. That's not the same as what we would have the B, A, C, D. If you have a cycle like this one, then I need a separate letter. So first A goes to X. Suppose X is not in this cycle or not in the in this S2, the final. So I need this one as a temp space. Just like when we do the swap, you need a temp location to store the old value. Now I'm going to say B now would be mapped to A. Now initially, right, I need to replace the A with B. But to avoid this one, now this time I don't have to replace A to B. So I'm going to say X now is mapped to B. So if I do this way here, so the map A, B, C, D. So A is mapped to X. B, C, D would still remain the same. Next, I'm going to map B to A. So this will be A here, and the others will remain the same. And then the last step, I'm going to map X to B. So this will be B, A, C, D. So that's what we want. Okay, so notice here, if you have a cycle, you need an extra variable to hold one of the variables. And then you're going to the chain reaction. So if this one has been replaced, right, to X, then all others, right, you can say B replaced to A and others to B and so on. Eventually, the last one will go back to what it wants to be set. So we need an extra space. So a temp location. So if S2 has Well, S2, the length can go up to 10.5. So could have all the letters, lowercase, uppercase. If S2 has already taken all the 52 letters, then we would be in trouble. You cannot find such a letter. So in that case, you cannot do it. Or sometimes you can do this one. So I do have this cycle here, A to B, B to A, and I do have another one. X also goes to B. So there is A to B, there is another X to B, but this X to B is not in the cycle. Just like this one here, A to B, right? So this just one way, the mapping. One letter is mapped to another one. So here X is mapped to B here. So I can take this one as my helper, right? Initially, I'm going to say A replaced by X. And then once the loop has done, I'm going to just apply this one. This one, anyway, you have to do it. So this will kind of help what I did here. So for this question, actually, you're going to identify the cycles. If you have a cycle by itself, we say the simple cycle, then you need an extra location and extra step to finish the mapping. But if you have a cycle and then just have another one, so here A to B, B to A, that's cycle, and you have another one adding to this cycle, then you can avoid such the extra step. It does not matter, but the cycle may be long and you have more than one such edges come into such a element in the cycle. Does not help, because anyway, for the cycle, I just need one extra storage. And this can be done with help of just one or two, and just any one is enough. So here, I'm going to have the mapping. So actually, I'm going to first build a map for all the letters in S1 and to S2. If a letter stays the same, this letter stays the same here, then I don't bother to deal with them. But if in the same location, the letter does not change, then I'm going to ignore that one. And since we have defined, dealt with the situation, right? If you have a dot here, does not change, another place dot change to say $, then this is we're in trouble, right? So that would be easy to handle. And almost all the input cases, right, they will not have these easy cases that have been filled out. So now we're going to say build a map for all the letters if they have changed. So from star to triangle, then we're going to build the map. And we're going to find out among all the map, right? We're going to find out cycles. Or here we're going to say maybe using the path, maybe more accurate. So a cycle, it's a special path that will just come back to itself. And we have some path like this one. And the path may not just be just a length one. Could be, I can go from X to Y and Y to Z, Z to W. Does not go back to X. So that is a path. Okay, all the X's will go to Y, all the Y's would go to Z, and all the Z's will go to W. Or the order does not matter, right? So we're going to just say replace all the Z's to W first, and then replace the Y's with W. Z and replace X with the Y's. So you still see the Y's, but these guys will be done first. All right, okay, so we're going to find the path. If in the path we have a cycle, then we'll be careful. For a simple path that is just by itself, no other letters will be mapped to any letter in this cycle, then we need one extra step. If we do some other edges connecting from one letter to a letter in the cycle, then we don't have to add an extra move. So basically, that's what we want to do. So building from the map actually would go from just 52 letters to 52 letters. So it's a mapping quite simple. You don't have to actually spend much effort. It's the size is rather small. And then find out the path for each letter. And we're going to here ignore the path. We say the self included the cycle. So a cycle with just one element, we're going to ignore it. That is also the case for pretty much all the USACO questions at gold level even. Of course, including silver level, we try to avoid the edges. You start from one node and come back to the self. Right? Recall in your memory. For the USACO questions, you worked in the silver level. We don't have edges like this. Normally, we read an edge, right? We say going from connecting A and B, and A, B would be distinct nodes. But this could happen. So in this case, actually, that's still consistent. If a letter is mapped to self, we're going to ignore it, right? So here, B to B, ignore it. C to C, ignore it. Just to work with A to B. All right, so here, the idea is clear. Then let's see one implementation of this file, find and replace. Let's check the C++ version here. Build a map. This map is actually the 52 letters to the index in the alphabet. So lowercase would go from 0 through 25, and uppercase letters will go from 26 to 51. That does not, there should be a symbol, right? We'll have all the 52 letters, and then I can reference them using the index in this basic array. So it does not change for the queries. So I'm going to set it up before reading the queue. So now we're going to say for each query, we're going to read the two strings as one, the initial string as two, that's the final string. This is the map, the shuffle. Okay, not this map. Okay, this one is say all the letters if they have changed. So they say letter A, well, not the one letter here, A goes to next one. So from the S1 here goes to the letter in S2. So initially we're going to make this all to be -1. So that means we have not seen the rule for the, we'll call this one shuffle or the mapping. Now we're going to have the variable boolean. If it's this possible, sometimes it will be easy to check it is possible. Sometimes easy to check if it's impossible. For most of the cases, right, it will be unclear. We have to do more checking. So how do you know if it's impossible like this one here? In position J here, S1 has letter X, S2 has letter Y. Here, since I have this map at the beginning, right, I can just get the index. I don't have to check the letters. So just work with integers. If the two here, next X is not -1, that means we have seen the rule. The integer X in S1 is mapped to Y has been said before. If it's -1, that we have not seen it before. We have seen it before, but it's not Y. So we have two output for the same integer X. In that case, we know this is impossible. So that's a simple way to say this query, right? It's impossible. But most of the time, this is not the case, will not happen. So we're going to map X to Y here. So if you see integer X in S1, it should be mapped to integer Y in S2. Okay, so almost all the cases, this should be consistent. That's contradictory. Okay, so, and also in the process, we're going to also find all the distinct letters in S2. Why this is important? I need to make sure if this set, the size, if it's equal to 52, then I would be in trouble, right? Because I don't have an extra storage to hold the variable that I use for the swapping. So if S1 and S2 already equal, then that's easy. Also, this one is will be very, very rare. Also, if S1, S2 are not the same, but the HS, the set of the distinct letters in S2, if it's already 52, then you know it's impossible. There is no buffer room for swap. swap. Okay, so those two cases will be simple. Otherwise, for the string S1, string S2, we need to do more research, more checking, examination to see whether it is possible. If it is possible, find out how many steps. If it's impossible, then the answer would be just -1. Now, if it is possible, then we're going to do the following checking. So going from here to down here. Okay, that's a little long. So this is the in degree. In degree is in a graph how many edges will come to a node. So out degree is how many edges will go out from the current node. So initially, every one would be 0. So this counts the integers in S2 or the letters in S2. For each letter here, if next A is not -1, so here it does get mapped to a letter from S1 to S2. It's not -1, right? This includes the letter A points to one letter mapped to itself, right? Those are not considered here. So when we have not the same, then they will be not considered. So if it's not -1, that means there's mapping and not the same as A itself, then we know, right? The mapping goes from A to next A, and for the letter next A, there is in degree. All right, okay, so now we're going to say for each one here, each such mapping, I need to increase the number of operations by 1. For the path singular one, or we have the path, even though it is a cycle, right? We're going to also add it. Okay, now what comes next would be, we're going to find out the path. If we have a path that is a simple loop, then we need to add 1 extra move. So now for each one, we're going to find out whether it is a cycle. So for each one here, each letter, if the path number is 0, right? Initially is 0. If it's 0, that means, right, we have not assigned a path number to this one yet. So we have not visited this letter yet. So we're going to start a loop going from R here. Every time we're going to say, where does X is mapped to? So as long as X is not -1 and the path X is not 0, then you always find a new letter that will keep the path. So we start from R to next, assign the path of this letter or this node here to R+1 to avoid, because this one by default is 0. So make this at least 1 here. And then we're going to pass to the next one. So if X is still not -1 and then this one has not been processed, we're going to keep doing this one. So when the loop is done, either X is -1, that means it does not go out, does not continue the path, or X has been visited before, right? This one we're going to stop if it has been visited before. So could join another path or could just come back to the current path. If it comes back to the current path, then we have a loop. We don't worry about going join other cycles. So this will be just still a non-cyclic path. But we are concerned, or we are trying to find out the loop. Okay, if a loop has number of nodes, right, big than, or you could do 2. If it's single one, that's not a matter. If X comes back to R here and R is not next to R, so this will make sure, right, this is a cycle, but cycle length is at least 2. Now we're going to find out whether this is a simple loop. How do we know? If the in degree for each one in the path, right? If it's 1, then it is simple loop. So here, that's what I was talking about earlier. If I have simple loop, everyone has just in degree is 1, out degree is 1. Okay, but if you have, so going this way here, if you have another one coming here, so this is say X, but there is a W coming to X, then you know, right, for node X, the in degree is bigger than 1, then you know this is no longer a simple loop. You have others coming, and this W can help us to provide a temp storage when we do the swap. So if the integrity of any node in this path or the cycle. If it's bigger than 1, then simple loop is no longer true. So after we finish this, we're going to find out, right? If it is still a simple loop, we're going to add 1 extra move to answer. Otherwise, you don't. Again, if you have more than 1, does not matter. I just need 1 temp space to help the swapping. So when we're done here, we're going to have the answer for such one. And if it's impossible, the answer should be -1. Okay, so we have made this one right. Even though the impossible would be very rare, but maybe in one of the test cases, it could be the it's impossible. So even though it's rare, we still have to put that into consideration. Otherwise, we have done possible here, impossible here, and then we just print out the answer for each query, and then we're done. Okay, so that is for the first question, find and replace. Okay, if you have done this one, I would recommend take the gold version of this one. So in the gold version, each letter is not replaced by just a single letter in S2. Could it be a string? And then the difficulty level will go up. But still, it's a very interesting problem. Ben wrote this one. Now, question 2, following the directions. This one is actually a typical grid traversal. So we're given a grid size n+1 by n+1. But ignore the right boundary and then the bottom boundary. The n by n upper left corner actually would have the cells describing the number of cows in each. No, actually not. There is 1 cow in each cell, but each cell has a direction, either pointing to the right or pointing down. The cows can only go 2 ways, going east or going south, cannot go north or west. So each cow has to reach either the east boundary or the bottom boundary, and then they're going to stop, and then they're going to eat at the destination. And then each cow's cost is defined by this number, either on the right boundary or the bottom boundary. And we need to find out the total cost for all the cows. So there are n squared cows, and we need to find out the total. For one, that's easy, right? Now we have to, besides this one here, we're going to answer Q queries. For each query, we're going to change the direction, switch the direction of one of the directions in the grid. So switching between R and D. If it was R, now change to D. If it was D, now change to R. Now, after switching the direction, then some cows will change their destination. And we're going to update the total cost. So this one, don't try to do this one every time you start fresh, because if you start from fresh, right, you're going to visit n squared cows, find out eventually, right, for each cow, where does it end to? And you're going to add the cost together. So that would be n squared. If you do Q such queries, this would be too much, because n can go to 1500, Q can also go to 1500. So this one can go up to 15 cubed, and that is too big than the threshold 10.9. But actually, if you think about it, in questions like this one, when the complexity is too big, then normally there is way, or it is crying for you to say, okay, can you take advantage of the history? So for example, if I have the grid has been pre-calculated, so these are the costs on the right boundary, these are the costs on the bottom boundary. So if I change one of the cell, the direction, if it was to the right, now I need to change to down. Okay, so for all the cows that do not come to this location, they will not be affected. For example, right, for a cow like here, her cost does not change because this location, say, at position row R and column C, if this C is actually less than this column C, right, this cow will never come back, will go to west like this one. So the changing at RC does not affect this cow at all. The same thing, if I have another one, this one, the row index is bigger than this row here, it does not, no cow will ever go north, right? So this cow also would not be affected. Actually, the only affected region actually would be this part, right? Only those cows, the cows in those cells, right, have chance to reach the position R and C. So let's keep track. For each time, we're going to say at each location RC, we're going to count how many cows that will reach this cell. All right, and then if you change the direction of the cell RC, right, then we're going to affect only these guys. So it was going east, right? It has an original destination. It will go somewhere here, zigzag, right? East, south, east, south, like this one. So it eventually will reach this one here. So originally it has the count, the cost number. Now the cows in this room, right? So many cows, no, they will not reach this one. Rather, they're going to reach another one, zigzag, 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 reach this one here. So we're going to say for the this group of cows, minus or subtract the cost following this red path, but add the cost along this green path. Okay, so we're going to update along this one here, right? Update. So this one, right? You don't have these cows coming in, so minus here, minus, 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 right? For each one, update the number of cows reaching each cell along the red path. And for the green one, for each step, update, right? More cows will come to this one, update the number of the counts in this array. So this will actually will take big O(n) time. Why? Because you can only go east each time, right? Going east one step, so you're going to do n times, going down n times. So at most 2 n steps, you're going to reach either the east boundary or the south boundary. The same thing going down, that's big O(n). So big O(n) plus big O(n) update, that will take still big O(n), and you have Q queries. So this one is roughly big O(n) squared. They have the same magnitude. And for n squared, we can easily finish the calculation. But for O cubed, for big O(n) cubed, that's too expensive. So this one is a typical question. When the complexity is too high, we need to think about it. What advantage can we take? Basically, right, for some of the numbers or the information that we have calculated, can we reuse them? So here, to be more specific, right, when you change the direction of the cell RC, only the red path will be affected, and also the green path affected. All other locations, they would not be affected. So that saves the amount of the work. You don't have to painfully update the information for the n squared cells. You only need to update the information for at most big O(n) cells. So that's a reduction from big O(n) squared down to big O(n). And then you still do the queries queue, so that's much better than before. And with this, then the question is, after this one, then the rest is actually quite typical, the standard. Okay, so again, let's take a look at one implementation. Follow directions. Okay, I'm going to go through this Java version. And that's the size of grid. The directions for each cell, the weights here, even though we allocate space for the upper left corner n by n, but actually we only need the information on the right boundary and also the south boundary. But it's okay, since n is 1500, we can allocate the space. Okay, that's a small part, and then that will make later the multiplication straightforward, symmetric. Okay, just keep in mind, right? Only the weights on the right boundary and also the south boundary will matter. All others, we're going to make it just 0. So read the information for the directions. So this y index actually would be for the rows. And for each row, we're going to read one string and convert into an array of characters. So this is for row y, going from 0 through n minus 1. And then the last one, the row n, column n, actually it's for the weight for the right border. So we're going to read one string of length n, and then we have one extra integer that is for row y and column n. So we have n times n plus 1 entries read for this part. And we're going to read the, well, the cost actually. Cost per cow for the bottom border. So this is the south border here. And here we're going to just read n numbers. And this would be row n, column 0, column 1, all the way through column n minus 1. And we don't have the lower right corner. That one is never used. So it's like this is a square. We're going to use this right boundary. We're going to use the south boundary, but this location would never be used. Okay, so now we're going to find out the number of the cows that can reach each cell here. And again, we're going to make this one n plus 1 by n plus 1. Actually, we'll only use the actually everything else except this bottom one. We're going to see how many cows will reach the right boundary, how many cows will reach the south boundary. And then the cost will be the number of cows reach each cell here times the unit cost per cow in each cell, and add them together. That's the total cost. So initial cost will be like this one. That's the answer for each row, for each column here. If you have not reached the east boundary or the south boundary, we're going to say you can keep going east. That's going east here, going right, or going south. Going east, you're going to say the column index will increase by 1. Going south, you're going to increase the row index by 1. So going down here, right, you're going to say the number of cows at this y and x can all come to the cell at east direction. All the cows at y, x can go to the cell at y plus 1 and x. If we do have reached the boundary, either the bottom boundary or the right boundary, then we're going to use the number of cows reaching the cell times the unit cost. And this should be added to the total answer. So when we're done for this one, we have the initial cost. That's part of the answer here. It says the original value of cost followed by the cost after each for each query. So the answer actually has q plus 1 lines. Now we're going to do this one for every query, and then we're going to process the queries one by one independently. Actually, not independent. They're going to be processed in order. Okay, so read the row and column indices and make it 0 index. So here, because we have done started from 0, so here this is 0 index minus 1. Here in the input, they're all 1 index, so be consistent. Next, we're going to follow the path. This is the old path, zigzag, zigzag, right, until it will reach either the east boundary or the south boundary. And then all the the contribution and this path actually should be subtracted from the answer, the previous one. So here we're going to run a loop, start from y and x here. As long as the v and u do not reach the boundary, we're going to keep running. So this is just a simple loop. So here, as long as v is not equal to n and u is not equal to n, then it is still in the interior in this black rectangle. So if it goes east, right, u would increase by 1, otherwise v would increase by 1. Each time zigzag, one of them has to increase by 1, and we're going to say subtract the number of the cows from this y-axis cell. That is straightforward. At the end, we're going to say, after it reaches the boundary, we're going to say the new cost. Actually, we're going to subtract the number of the cows reaching this location times the unit cost at this. This is once the loop, while loop is done, VU would be at the boundary, either the south boundary or the east boundary. And we're going to add the country. Before we add the contribution, we have to switch the direction. So if it was red, now it's D. If it was D, now it's red. Now we're going to say for the new path, we're going to update again the number of the cows that will reach each cell on this path. Again, zigzag. So roughly the same process, but change from minus to plus. And then also, since now more cows would reach this destination, so I'm going to say this times the unit cost at this destination. So this is our new cost after we have changed the direction at this cell at y and x. So here the complexity, there are q iterations. This part, the complexity is big O n, right? At most n directions going down and steps going east. The same thing here, big O n going down and east. So overall, that's big O n inside here, and then outside that's q. So the complexity is big O n times q, which is perfect for this setting when they are no more than 1500. Actually, even when n and q, they can go to say 3000. That's more typical setup for silver problems in the grid. Okay, so then this one could be done easily. Question 3. Among the 3 questions, actually, this one could be easy if you see the a important but still simple observation. So Bessie started from position 0 here, and she would spend t seconds. Every second, she would either go east or west. After t seconds, she would be back at 0. Now we have recorded the number of times Bessie has crossed the midpoint, the half points, 0.5, 1.5, and so on, all the way through n minus 1.5. Bessie has never went beyond 0 to the left or beyond n. So she would cross at most n minus 1 plus 0.5. So going from, she always stayed inside 0 here, 1, 2, all the way through, this is n. So she would cross the half point 0.5 and 1.5, 2.5, and also the last one should be n minus 1 plus 0.5. She would never go beyond this one. She would never go beyond this one. So we have an array here going from a0 through an minus 1. Each number records the number of times Bessie has crossed the corresponding half points. So for ai, that is how many times crossed ai plus 0.5. So ai corresponds to I plus 0.5. So here I goes from 0 through n minus 1. Perfect. Now we're going to try to recover one such way Bessie can go back and forth, right, for the t seconds, eventually coming back to 0, satisfying going through these half points at exactly the ai times, And there is another restriction. The number of turns would be minimum. Okay, the number of turns must be minimal. So this means if for example, so this is a I and this is I plus 1. This is I minus 1. So this half point, if Bessie has crossed this half point I minus 1.5, less than the number of times cross this one here, then you don't want to turn over here. If this AI minus 1 is less than AI here, Bessie would never turn around at this one, because you can always, since AI is bigger, you can always replace it with another one come back. Because if you do this one, you're going to lower this count, right? The AI here one more time, so you don't have to do one more time. So here, if I use the red one, you're going to do like this. And if I have more here, right, you have to take one more round like this one and come back this. So here, turn around this one and this one turn around, right? That's unnecessary. I can merge them together into one, so it can reduce the number of turns. So that's the observation. If AI minus 1 is less than this one here, you should always continue. You'll never turn around when this AI minus 1 is less than AI. You never turn around, turn left at AI. Turn left at point I here. Okay, that is one observation. And also another observation to find out the minimum number of turns, actually, this will be helpful. So for, again, this is I minus 1, that's I, and this is I plus 1. Let me use triangle here. So again, if AI minus 1 is less than AI here. Oh, by the way, one more thing, right? Since Bessie started from 0 and come back to 0, so for every point in the middle, all the half points, Bessie must have passed even number of times, right? Because she has to come back to 0. So going this way and must go back. So all the AIs must be even. Okay, that is for sure. And all the test cases, there is no exception. Okay, if AI is less, AI minus 1 is less than AI, then you know Bessie will cross this one going east half of the times, right? Divided by 2. And then you have another half times going west. This one, again, passing this point, half point, right? Bessie has to cross half of the times going this way here. This number is less than this here. So even though we can do, say, R and R without turning, but this will just count, as we said, right? You never turn around at this one here. So when you do the R, you always keep going. So even though you follow the R, follow this R by this R, right? This will only count so many times. But to make it a I over 2 here, then you must have some other times going this way here. So that must come from, so from position I plus 2, this one was going left. This one is also going left. Oh, actually, you don't have to. This one can come here and turn left and then continue R. So this was going from R and then R, and this one is left and R. So you must have AI over 2 minus AI minus 1 over 2 so many times of the L and R. That is for sure, right? Because you cannot make going through this right followed by just RR. Since RR can only do AI minus 1 over 2 times. So if you do that one, that would make it R. That's good. We want to minimize the number of the turns, but that's not enough. This number is less than this one here. So you have to do the extra so many times that is going from I plus 1 down to I, and then continue this going east direction. So arrow followed by R. So if you do so, that will be the number, will be a turnaround. So here we see if the two adjacent numbers, AI minus 1 to AI, if this one is less, then you know, right, you have to do this. What about the other way? If AI minus 1 is bigger, then you're going to do actually the same thing. So this one will go west again half of the times. And this one also you have to go left, right, half of times. So if you do just arrow here followed by another arrow, that's great, no turn. But that's not enough, right? Arrow is not enough. So you must have some other times, this one is right and then left. So you must have the right and then followed by the arrow. Then you can have more number of times passing through this half point at I minus 1 plus 0.5. So this also will count the number of turns. And here should be the same, AI minus 1 over 2 minus AI over 2. So actually that's what we want to do. Find out the number of the minimum turns would be, say, if the number is less than the next one. So this one, you'll always keep going to the east, going right. You never turn left, turn around in before you reach the number that is bigger. The same thing here, if the left is bigger, then you always keep going left. So that is actually the principle. If you can keep, you can going left, right, keep going left. If you can go right, keep going right. So that will just minimize the number of turns. So here for the silver level, you don't have to count the number of times, the number of the ways to achieve this visit every half point with the AI number, and also maintaining the minimum number of turns. Here we just need to provide 1. So here using the principle, whenever you can, just keep going along the direction. So initially when we start from 0, we're going to keep going right until we cannot. Once we turn it around, we're going to say keep going left all the way until we cannot. So when do we know we cannot going right? Every time we pass through a point here, we're going to decrease the value, right? We pass the 1, we're going to decrease the count here, pass this value, decrease this one. So whenever we pass through, we're going to decrease it until we find out the AI that is not positive, then we're going to stop. We have to turn around. Okay, also, if you say, I'm keeping doing left, what if I'm at a point to say I here, but at this I minus 1, right? Passing this half point, the AI minus 1 is already 1, then don't go left first. If you still have business on the right to finish. So if the count right AI or to the right, the numbers are still positive, then don't keep going left. You can't, because if this is 1, that's the last time you have to use to go back to 0. So in this case, right, you have to turn around, finish the business on the right first, and then when all these become 0, then just go back. So apply this heuristic, then we can find out one answer. So let's see again, one answer. This one actually is quite short. Actually, you can finish with in 37 lines of code. And that's number of the crossing points, half points. And A, actually, we're going to make it n plus 1 so that I know the number of times you cross n plus 0.5 is 0. Actually, you never go beyond n. So, right, we do have another one. So this one is just to help us to make sure in the following loops, you don't go out of bounds. So here, that's to read from the input, the number of times cross each half point here. That's the output, because we need to display one such route. Here, we would recommend using a string build if you write in C++, Java, because if you print n times, it will take more time. But of course, for this one, it's not too bad. But if you keep a string, every time you append one character, that will be not efficient. Okay, we have seen those issues before. So use a string builder, or you can use an array list to append one letter each time. So start from position I, that's the current location. If I is not 0, or if AI is not 0, so we're going to, so AI is fine to cross the I plus 0.5. So we're going to go right as far as possible. If AI is bigger than 1, you have to make sure this is at least 2, right? Because you have to go right and you have to come back. So this number must be bigger than 2. So if it's possible for us to go right, keep going right. So append one letter R to the route here. And since we pass this point, half point I plus 0.5, right? So decrease the number by 1. And since we go right, we're going to increase I by 1. Keep doing this one until this AI is not bigger than 1. Actually, cannot be 1. Remember, right? Every time we go through this one here, come back to itself, it will be even times. So AI in this case would be make it even, but in the process going east, right? That's not going to guarantee 1. But when you come back, you're going to go through the same point twice. So we're going to make sure it is positive. Now, if you have reached the point, so the AI is 0, remember, right? AN is 0. So for sure, you're going to stop. Then you're going to turn left. And then you're going to, once you turn left, you're going to go left as far as possible. If this at point I, right, AI minus 1 is positive. Okay, and then actually more careful. If this one is 1, be careful, right? Finish the business on the right first and then turn left. Only when all the integers on the right from AI and the big right, they have all become 0, then you can go left if AI minus 1 is 1, because that's the last chance you can cross the point I minus 1 plus 0.5. So here, if I is positive, then you have a neighbor on the left. If this one is bigger than 1, then you can continue, right? Or if this one is 1, but all the things on the right is 0, AI is 0, then you cannot go right anymore. Then you have to turn left. And you have to go left. So we're going to append left here. This time you have to, the order, right? You have to go down by 1, and then you're going to decrease the AI. Because suppose if we are at point I, the AI is actually not the point on the left. The point, half point is actually on the right. So when we go left, we have to address the half point on the right. So swap the order of the 2. Okay, once we have applied the principle, if you can go right, always go right. If you can go left, always go left. So this will minimize the number of the turns. Okay, and then at the end, we'll just print out this one here. Since the answer does not have to be unique, then you need to write a checker. So this is a typical way to write the checker, and then that's the input file, that's the reference solution, and that's the solution we just generate. So for example, if I run it, so actually this would be 6. Okay, so the route, and will generate the answers for each case. X dot in, X dot out, that's the reference solution, and X dot out 2 is the answer we just generated. And how do we know the answer X dot out 2, right, is correct? So we're going to make sure, okay, read the input here. That's the number of times you need to cross each half point by AI times, AX times. And then the reference solution will give you the number of the turns, right? The minimum number of turns. Okay, minimum number of turns would be easy, right? You're going to check if at each J is different from J minus 1, then you know there is a turn. So we're going to read the reference solution to decide the minimum number of the turns. Now we're going to read the answer. First, we're going to also check the turns. J and J minus 1, if they're different, then we know there is a turn. So turns and turns 2 should be the same. Otherwise, this is incorrect. And that's not enough. We have to also check your solution. Does it pass each half point by this number bx, right? B and A must be the same. If you say, I do have the minimum number of turns, but I did not pass each half point by the specified number of times, then that's still incorrect. So here, how do you know this one? Every time, roughly the same, right? If I say going left, then my current position will decrease by 1, and I'm going to say, I just passed this current plus 0.5, so we're going to say increase the frequency, right, for this one by 1. If I go right, I need to increase this one first because the half point is on the right, and then we're going to increase the current position. So this one is actually based roughly the same as this what we did here. And then once you have A and B, you're going to check whether the two arrays A, B are the same, as well as the turns should be the same. And then you can print whether each one is correct. So if you run it this here, you're going to see here, for all the test cases, 2 pieces are both correct, then you know your answer is correct. So you don't have to check your answer with the reference answer, whether they are the same. No, actually, it does not have to. So just write your own checker. Of course, you can always submit to the USACO to see whether your answer is correct. But I would recommend you to provide your own check later when you try to write your own problems, USACO style questions. You also need to write the checker. Okay, so for this round, the questions actually are not that scary, as many of you have expressed when you had the experience working on questions in season 21 and 22. Many said, okay, it was harder. I had no idea what to do. But for this round, at least I have some idea, even though I may not be able to pass enough cases to get the promotion, but I feel much better. That is good. Okay, keep practicing. That's the only way to make you more confident, more fluent, and more efficient, especially during maybe the 1 week or 10 days before the contest. Warm up to the best status so you can have the efficiency, the confidence to solve the questions and get your goal achieved. All right, with this, I'll stop here. I'll see you guys later.